Here's our discussion about why the real and imaginary parts of a complex solution to a linear system are also both solutions of the linear system. Here is our linear system. A is a matrix with real coefficients, but it has a complex eigenvalue lambda, real part A, imaginary part B, and corresponding complex eigenvector V, so that A times the eigenvector is equal to lambda times the eigenvector. The claim is that the function of the form e to the lambda t times v will solve the differential equation, the linear system. Any complex valued function has a real valued part plus I times its imaginary part. Y1 of t and y2 of t are real valued functions. The only I is sitting here. This is the form of a complex valued function, which y of t is. It'll have a real part, an imaginary part. The real part is just a real valued function of time. The imaginary part is a real valued function of time. I'm going to show that this is a solution, and I'm going to show that y1 and y2 are also solutions of the same system. That's the plan. So first we show that this guy is a solution, okay? Here's our linear system. I've written it one more time. We know that A times V is equal to lambda V. We take the derivative of our solution, which is of this form. Here it is. We're taking its derivative with respect to t. The only t in the whole expression is here, an exponent of an exponential. And so the derivative of e to the lambda t is just lambda e to the lambda t. And the v, vector v, is just a constant, and it sits there, goes along for the ride. The commutative property says that, hey, lambda is a real number, and for every value of t, e to the lambda t is a real number. Well, I'm sorry, a complex number. Lambda is complex. This is complex. Complex numbers also have the commutative property. It doesn't matter what order you multiply them in, you still get the same result. And so here you see me switching the order, e to the lambda t first, times lambda. Using parentheses just to group these, I now observe that lambda v is recognizable. Lambda v can be replaced with av. We've replaced it here with av. And then continuing down here, again I'm going to, well, this isn't the commutative property, this is a property of matrix multiplication. A scalar, this is a complex scalar, for every value of t we get a complex number, but a scalar times a matrix, which is being multiplied by a vector, can sit out front, or it can come inside and multiply the vector first, so we can allow this to happen first, and then multiply by the matrix A. This is a property of linear algebra and matrices, and so we are allowed to do this. And then we observe that the term inside parentheses is what we called y of t to begin with, and we have a statement that says the derivative of y with respect to t equals ay, and anything that satisfies that property is a solution. Anytime you have a vector valued function that you differentiate with respect to t and end up with a times that same vector valued function, such a function is called a solution. In this case, it's a complex valued solution. It has a real and imaginary part, but it is a solution. And so lambda e to the lambda tv is a solution, but it's a complex vector function, and so we can write it with its real part and imaginary part for some real valued functions y1 and y2 of t. So we know, I've already shown on the previous slide, that this is a true statement. The derivative of y is equal to a times y. But y is a complex valued function, so it is of the form some function y1 of t plus I times some y2 of t. It has to have a real part and an imaginary part if it's a complex valued function. And replacing the same expression for y of t here, I'm missing a little parentheses here, I have a times y1 of t plus I y2 of t. The derivative is a linear operator. The derivative of a sum of two expressions is equal to the derivative of the first expression plus constant times the derivative of the second expression. Similarly, the way matrix multiplication works, a matrix times a sum of two vectors is equal to the matrix times the first vector plus the matrix times the second vector. We look at this expression and we observe that, hey, here's a real valued function here, and here's a real valued function here. Here's an imaginary, purely imaginary valued function here, and here purely imaginary. The only way we can have equality is if the real parts must be equal, and so I'll just draw a line. These two, these are the real parts, they must be equal. And the imaginary parts, these two parts must be equal. When two complex numbers are equal, they're only equal when their real parts and imaginary parts are equal. And this implies that the derivative of y1 of t must equal ay1, and the derivative of y2 of t must equal ay2. I'll put the t in there. And anything that satisfies these equations are solutions of our original equation star. So it turns out that y1 of t must be a function that when differentiated gives me a times y1, and y2 must be a function that when differentiated gives me a times y2. One example from our textbook, just to verify that, here's a linear system. Coefficient matrix is A. This is from section 3.4 in our book. We're given, where we solve for an eigenvalue minus 2 plus 3i and the corresponding eigenvector I1. Here is our solution e to the lambda t v, but e to the lambda t is broken up as e to the minus 2t times e to the 3ti. I'm not showing you the complex function algebra that, well, it's just complex numbers. But when I multiply this using Euler's formula times this and clean everything up, I end up with a complex valued function. Here's its real part, and I times its imaginary part. No surprise there. And according to what I've just shown you, this guy I can label as y1. This is the real part, that's y1 of t. And this piece is y2 of t. I'm only going to demonstrate that y1 of t is a solution, and if you're not convinced, you need to do the same thing to convince yourself that y2 of t is a solution. So here I'm showing y1 of t to be a solution. I take its derivative. It is a product rule. And so the derivative of the first, I bring down a minus 2, so I have 2 e to the minus 2t sine 3t. Then I'm differentiating this part. I bring the 3 in front. This sine turns into a cosine, and I have minus 3 e to the minus 2t cosine 3t. This is also a product rule. the derivative of the first brings down the minus 2 e to the minus 2t. The cosine 3t goes along for the ride. And then the derivative of the cosine 3t, which produces a negative sign, minus 3 e to the minus 2t sine 3t. So there's the derivative of y1. What's a times y1? Well, a is minus 2 minus 3, 3 minus 2. Here is y1 written out again. I take a row times this column. The minus 2 multiplies the minus here to give me a positive 2 e to the minus 2t sine 3t. The minus 3 multiplies this term to give me a minus 3 e to the minus 2 cosine 3t. And we see that's exactly what we have here. This one does it in reverse order. This row times this column gives me 3 times this minus sign, so negative 3 e to the minus 2t sine 3t, minus 2 e to the minus 2t cosine 3t. That's minus being multiplied by this term. And this is just in reverse order. Here we have minus 2 e to the minus 2t cosine. Here we have minus 3 e to the minus 2t sine. Okay? So sure enough, this guy is a solution. And in the exact same manner, you'll show that this is a solution. So that is why the real and imaginary parts of a complex valued solution are also solutions. And we use these to build our general real valued solution, because that's what we're after. We want a real valued function, the general solution of a real valued function. Even though this is a perfectly good solution, it lives in the complex plane. That's not what we want. But we're able to pull off its two real and imaginary parts, which are both real valued functions, and use them. Okay, good luck. Thanks.